Hi everyone, good day to you. Welcome to FIT3143 Parallel Computing Week 9 Pre-Laboratory video. So in Week 9 lab activities, we will be exploring the Message Passing Interface or MPI Virtual Topology along with Message Passing Interface, MPI, Master and Slave um, methods of communicating. All right. So let's get straight to the code and the specifications and our reference source for today's discussion. All right. So I'm going to share the screen now. Okay. So over here in this week's lab, maybe I should open the lab file first. Okay. So there are several tasks for you to undertake in this week's lab. All right. The first one being understanding a 2D Cartesian grid using MPI, and we have provided you a worked example here. All right, so I will go through the code with you all today, and I will explain to you all what is the idea of using an MPI virtual topology and how this code provides an example. Now, this particular sample code, the worked example, doesn't include communication. How do you send messages between the adjacent nodes once you've created a topology? I will add that code into today's video, and then I will attach the code separately in the video description and also in Moodle for you all to refer to later on. Okay, and then in task 2, you were asked to then implement, expand on the task 1 code to perform some form of communication and exchange of messages. And should the exchange of messages, should the values of the exchange messages meets a certain matching value, okay, or the values are matching, then each node will log the value. So this has some similarities to the assignment 2 specifications, but it's not exactly the same. But by doing this task, then you'll be much more better positioned to solve assignment 2 should you actually decide to use virtual topology for the assignment 2, MPI virtual topology. So task 2 is something that you are required to complete together with your teammate. And then in task 3, we will go into master slave program in MPI. Again, in task 3 is a worked example. So just like task 1, you're not required to solve any particular problem for task 3. It's just a matter of compiling the code and understanding the code. All right, and then we have provided a sample code here. So I'll explain to you all later on the key functions. And then later on in task 4, you are asked to then expand the code in task 3 to do some additional activities. And then we have provided your optional bonus activity here to do a 3D Cartesian topology, but this is optional bonus, and this is something you can do based on your own, yours and your teammates' interests. Okay. So let's go to the interesting part here on MPI virtual topology. Okay, today's discussion is largely based on the sample code and also on the materials prepared by Mary Thomas from the Computational Science Research Center at San Diego State University. So I think Mary has prepared a very good explanation on MPI communicators and topologies, and I would like to refer to her slides and also on her sample code to explain to you all how MPI topologies work and how you can actually make it to good use. All right, and based on her sample code, I will then add on to additional example on how you can actually exchange messages between neighborhood nodes. All right, so I will provide a link to the PDF file for the slides by Mary Thomas, so you can refer to them. And now we're not going to cover all of the sample code in this PDF. It's quite lengthy, but I'll cover the key ones which are related to your lab activities today and might come in handy for your assignment 2 as well. Okay, so let me just largely go through first the notes inside this particular PDF file over here. So MPI supports processing elements grouping capability. The P here means processing elements. So you can actually organize, you can actually create groups to organize your processing elements. And then we can also use these communication groups to create virtual topologies, which we will go on later on, to allow for for some form of custom communication, or if, as what I mentioned here, for some safety purposes. All right, and typically some of the commonly used MPI group routines are given here. We have not used any of these functions in our lab activities or our in lecture code discussion so far, but nevertheless MPI provides these functions to allow you to get information about the MPI group, and also to create your own custom group also. All right. Okay, so this particular example over here by Mary, what she has done is that she just created, I can zoom in a bit. Okay, she's just created, the code starts from here and the code ends here. So she's just using a normal, the normal local, the intra communicator. All right, and after that, from here, you're just doing a send receive between the processors in the group. So generally we have a one-dimensional set of processors, okay, P0 to P8, and each of them are just sending messages, I think between their neighborhood nodes, if I'm not mistaken. Okay, but that's the idea of it. All right, it's a very simple thing. You've done this before already. Yes. Okay, it's a send receive operation. Okay. Now, what Mary then did is that she expanded this code by using a particular unique function called MPI, MPI group include, and MPI com create. So now you create your own communicator, and by specifying the group that you want to pass into your local communicator inside here. And inside here, we can actually specify which processes we want to put into our custom group. So in a nutshell, what Mary is doing over here in her code, okay, I'm just skimming through this code because it's not related to what we want to do in this week's lab, but nevertheless, I'm just quickly going through, so at least to give you an idea on what this code is trying to do. Generally, what this code does is that it actually groups the intra communicator into subgroups over here. Okay, so each subgroup will have now a new sub communicator, and then you can then use the subgroup communicator. Like you do an MPI broadcast, you only broadcast within the processors in this group over here. That is what the code above is trying to actually achieve. And you can try this, you can copy and paste. You can just copy and paste the code into your own code editor, and then you can compile the code. There are one or two minor bugs in I think specifically with regards to the use of the ampersand symbol to specify the conversion specifier over here. But other than that, the code is fine. All right. Okay, so this is generally what the early part of the PDF files that discuss about how you can actually create your own subgroup within an intra communicator over here. Now, the part that we want to go into in today's pre-lab video is on the MPI virtual topologies. Now, as the name implies, virtual topologies, okay, there's no relation between the physical structure of the parallel machine and the process topology. Virtual topologies are built upon MPI communicators and groups, and it is programmed by the application developer. So technically, MPI virtual topology just creates a virtual topology on top of your current physical topology. It doesn't physically alter your parallel, your distributed parallel computing architecture in MPI. All right, it just creates a virtual topology which you can benefit in terms of how you want to communicate between your neighborhood nodes or between other nodes. So there are two types of topologies, Cartesian and graphs. We'll be covering Cartesian in week 9 lab. And then in Cartesian, we can create 1D, 2D, and 3D. Okay, we'll be doing 1D in our task, and 3D is something for you all to consider as an optional bonus activity. All right, so why is it, what is the benefit of doing MPI topologies? Okay, the benefit are, it is useful for applications with specific communication patterns. So if you refer back to our assignment, okay, if you look at our assignment over here, so our assignment may benefit, not necessarily it does benefit, it may benefit from using a virtual topology, all right? But again, if you refer to the assignment 2 description video, you realize that it is not necessarily, it's not a must for you all to actually use virtual topologies. You can actually compute your adjacent nodes manually. So we have done that assignment 2 description. So I would implore you all to look at the assignment 2 video description in the assessment section in Moodle to get better understanding on that aspect. Okay, but nevertheless, having a virtual, by using MPI virtual topology functions, you do have some convenience on creating creating an MPI program with specific communication patterns. And also it can actually to some extent improve communication efficiency. All right. Okay. So the key functions that we will be going through today in based on the code I'm going to discuss shortly is MPI dimensions create, or they use the abbreviation DIMS create over here, MPI cut create, MPI cut coordinates. MPI cut sub is to create a subgroup within a Cartesian communicator. So this is something that we were not going to discuss in today's PLab video, and it's not also covered. It is not covered in this week's lab, but this is something that you can explore later on in the PDF slides. These PDF slides at your own interest to expand knowledge further. And then we will also look into MPI cut shift to find the processor neighbors. All right. Okay. So the first function, MPI dimensions create. MPI dimensions create takes in 3 arguments. Okay, the number of nodes, okay, the number of processors in your intra communicator, the dimension of your Cartesian, whether it's 1D, 2D, or 3D. So typically it's either 1, 2, or 3. Okay, and then an array to the array containing the dimension values. So if it's a 1D if it's a 1D dimension, then you only pass in an array of 1 element. If it's a 2D dimension, you pass in an array with 2 elements. All right. Okay, and this is something that is written. You pass in a pointer to an array, and then it populates the array with the grid architecture. So what dimensions create does is that it actually creates for you a grid based on the number of nodes in the particular architecture. So if you pass in 12 processors, 12 MPI processors inside here, and you want it to be a 2D dimension, it will create for you a 2D grid. Probably it'll be a 3x4 or a 4x3 grid. Okay, so so as he says, it creates a 1. Okay, so this is how it works. But if you specify the values here to be 0, then naturally it will create the best grid for you. But if you specify the exact values, then it will create a according grid value for you. So we will look at the example code later on about this. Okay, MPI cut create is the main function. So MPI cut create is the one that creates the virtual topology in a Cartesian grid. All right, processing elements are processed in order from 0 to last element. Okay, based on how you want your grid to take shape, whether it's a 1D, 2D, or 3D grid, a 3D grid. Sorry. So this function takes in 1, 2, 3, 4, 5, 6 arguments. Okay, the first argument is your current communicator, the intra communicator. The second argument is the number of dimensions of the Cartesian grid. The third argument is the array to the dimension. So these 2 elements are the third element here is populated by your earlier function. If you call this function, it is not necessarily to call this function. Okay, you can actually create your own. You can actually specify the size, the dimension in the array, and then you can pass in the array into this particular function over here. The fourth argument tells you whether or not the grid points periodic, which means that if you reach the leftmost node or the rightmost node or the top node or the bottom node, should this node communicate in a circular manner. All right, so that's what you specify. Reorder tells you that whether should you want to reorder the ranks in the Cartesian communicator. But before we put it to 1, most of the time it will not reorder, but sometimes if it finds that if it can improve the efficiency, it will reorder for you, and then it will return you back. So you can see here the last argument is an output argument. It will return you back a new communicator with the Cartesian topology. So this is a new function that you are learning in this week's lab, apart from the earlier function I mentioned just now. Okay, and then after that you have MPI cut coordinates. So MPI cut coordinates, as the name implies, if you pass in your rank, it returns you your corresponding coordinate value. All right, so example here, if I pass in my rank 1, it will return me the rank value 0, 1. If I pass in my rank 6, it will return me rank 1, 2. This is exactly the same like what we did in the assignment 2 description, there, whereby if you want to get your row and column position, what do? We take the rank divided by the column width. And then if you want to get the column position, we take the rank and then we divide it by the column width for the remainder. So for example, like here, in this particular case, our column width is what? 4. All right. So if I pass in the value 6, okay, so row position for value 6 is what? 6 divided by 4. The answer is 1. Column position for values for rank number 6, 6 divided by 4 for the remainder will give me an answer of 2. So my coordinate is 1, 2. So this function, if you go into the inner workings of this function, it does the same thing for you based on the created Cartesian. Okay, so that's what it does. Okay, and card sub, I will just briefly go through here. It just creates a partition communicator into subgroups. So this one is something for your own reading. We will not discuss this in this week's lab. Card shift, all right, returns the shifted source and destination rank given a shift direction and amount. So it tells you who are your neighborhood nodes. So generally you pass in your communicator of the Cartesian topology, the direction, whether are you looking at left or are you looking at a column direction or row direction, and then how much are you displacing? Are you looking at the immediate neighborhood node, or are you looking at 1 or 2 nodes ahead relative to your current node? And then it returns you the source and destination. It returns you the I and j value of the neighborhood. You pass in the source of you pass in your source in your source rank, and then you pass in the destination. You return you the rank of the destination process. I think we will do an example later on. I think it will give a much more better clarification over here. So I'm going to skip this code. This code is how they do cut create for 1D. This is how the example does it. What I want to discuss is MPI cut create for a 2-dimensional topology over here, which the output of this code is based on this example over here. So I'm going to go to the code here. So this code will be this code is provided to you all in the task 1 activity. All right, so if you look at task 1, this code is given to you already. This code is taken from there and it was slightly cleaned up to fix some minor bugs, and then it's given to you here. And I'm going to go through this code with you all now. Okay, so if you look at the given code, all right, so what we have here, I've declared some symbolic, I have a set of header variables over here, I mean header files, sorry. I've defined a few symbolic constants: shift row 0, shift column 1, displacement 1. We will see how it's used later on. And then here I'm creating a 2-dimensional Cartesian. So my m dimensions is 2. And then I specify a few variables to be used later on. And then I have my row columns, my row and column values. And then here you see I have this is MBI is neighborhood. Neighborhood. My neighborhood, my upper neighborhood for row, my lower neighborhood for I, my left neighborhood for column, my right neighborhood for column. So generally, later on, these variables will return to me, okay, these variables. So for example, like here, okay, let's say for P5, if I want to get my top, bottom, left, and right neighborhoods, these variables will store the rank values of my top, bottom, left, and right neighborhood ranks. Okay, that's the purpose of these variables. How do I use these variables? We will go into that shortly. Okay, and then this is my virtual topology communicator. So I initialize a new variable. I create a new variable of type MPI communicator, MPI com. So this is something new. We are doing some new MPI coding here. Okay, so you will add value to your knowledge in this particular topic. Okay, and the wrap around. Okay, and we have a dimension array over here. So we will look into the code how it's used later on. Okay, so this is standard MPI init com size com rank. You're familiar with this already. So if you run this code for a number of MPI processes, each process will have their own unique rank, and each process will know a number of processes in the intra communicator over here. Okay, This particular code by Mary, she also allows command line arguments, whereby you can pass in command line arguments, and that command line arguments is used to specify the dimensions of the grid. So you can see over here, all right, I've created an array. I've created an array of type integer. The array contains two elements, n dimensions. Okay, the n dimension is value is 2 here. So I can put 2 so I want to. But anyway, we are based on the sample code is given n dimension equal to 2 over here. Okay, this is perfectly fine. So the first, so this array can take in two values. So the first value tells you how many rows are there in my Cartesian. The second element tells me how many rows I want, how many columns I want to create for each row in the Cartesian. All right. Okay, then they put a fail-safe code here. If the number of rows and column doesn't match number of size, then it will exit. Okay, so this is just a command line argument. So which means that when I run MPI run, I pass in the MP value, something like that. Okay, and then I can pass in the MPI out application, and then I can pass in the command line arguments here, 4 and 3. So these 4 and these 3 are the command line arguments that will be captured by the rows and column variables over here. Okay, so I think by now, I guess many of you all also have knowledge in command line arguments already. I think we've done this in the previous lab exercises also, and also the previous PLAB videos. Okay, otherwise, if the command line argument is not 3, which means there's no common line arguments, then we specify the dimensions to be 0. So when I pass in these dimensions into here, when I pass in the dimensions into the third argument, if you don't specify common line arguments, and if this function checks that the values here are 0 for each row and column value, then it will return you. It will populate this array. It will populate this array with the best possible grid value. So these dimensions create, if the dimension values are 0 for the row and column, then you will populate the dimension value with the corresponding grid value based on the given size over here and the number of elements in this array. Okay, but if you already specified the rows and column you want, and when you call this function, it will not do anything. You'll just acknowledge, return you back the same content over here. Okay. So rank 0 prints out the dimension of the grid. All right. Now here the wraparound is used, as I mentioned over here. The wraparound is used to specify, again, n dims is 2. Okay. The wraparound is used to specify to tell that our periodic shift is false. So we put my wraparound 0, my wraparound 1. Both of them will have the value 0. This is also equivalent to me doing like this. I mean, it's just simplifying the code a bit. Okay, same thing. All right, I'm specifying the wraparound for the rows and the columns to be 0, which means that it will remain to be a flat 2D Cartesian grid. Had I put this to be 1, then it will be a circular grid, which means that this particular Stack Overflow actually explains it properly. The card create period argument. Okay, so what does the card create period argument do? So the period argument specifies whether the n dimension is periodic. Okay, that is whether the coordinate 0 in dimension n is a neighbor to the n max. All right. So for example, like let's say if your n dimensions is equals to 1, then having a single dimension period false means that the topology looks like a line of workers. Otherwise, you got a ring. Let's look at 2, because we are creating a grid here, a 2D grid. Okay, if the dimensions is 2 and the period is false, you will get a square. If the period is true, you will get a cylinder. So which means, let's say we go back to this example over here again. If you specify the cut in the MPI cut create function, if you specify the periods to be false, it will appear to be a flat 2D grid. But if you specify the periods to be true over here, which means that your P0 can also the P0's neighbor can also go all the way to P3 and vice versa. You can have a ring topology over here. So it becomes like a cylinder. So it becomes something like a cylinder over here. So we have like a cylinder. So maybe, and then we have, So we have P0, P1, P2, and P3. So it's like a cylinder-based grid. They can all communicate. I mean, the topology is such that it represents it as a ring-based 2D map. Okay, but in our example here, we are not looking at that context. So in our example, the period is false. So going back to the code, okay, so here we specify the periodic shift to be false. Now the reorder is 1, as I mentioned. So the reorder, if you go to MPI cut create, okay, so the MPI cut create, okay, specifies that, okay, returns a handle. If the reorder is false, then the rank of each, maybe I should zoom in a bit. If the reorder is false, then the rank of each process in the new group is identical to the rank in the main communicator. Otherwise, the function may reorder the processes to choose a good embedding of the virtual topology into the physical machine. Now, in my experience, we put it to true, but so far, in my experience using Cartesian, the reordering has not made a much impact. I mean, the rank numbers are still the same as the intra-communicator rank value. So by default, you can just put it to true, okay? So in this case, it's put to 1 or true. So now, I call MPI cut create. I pass in my current communicator. This is my intra-communicator. NDIMS is 2. Okay, NDIMS here is based on the variable 2. Okay, and then after that, pass in the array. So remember, this array contains the grid size, whether it's a 3x4, 4x3, depending on the number of processes. So as I mentioned over here, either you can populate it manually, or you can specify it to be 0, and then you call dims create, and then based on number of size, it will create for you the best grid fitting. All right. And then after that, sorry, I jumped to the wrong function. Okay, and then wrap around. So wrap around is the reordering. We don't need to have a circular 2D grid, so or a cylindrical 2D grid. So we put it with false. They're all zeros over here. Reorder by default is 1, and then the most important thing, it will return you back so you see this is the output argument. All of these are input arguments. So you pass in the address of your communicator variable. It returns you like a handle or a pointer to your new communicator. All right. Okay. So if no error, then if the error returns you, if the MPI cut create returns you a value which is different than 0, then you have some problems over here. But this is rare, but it's just there for a fail-safe method. Okay. Now, after you have created cut create, this communicator. Now let me explain again. The cut create doesn't physically change your MPI processor's architecture. All right. What it does is it just creates a 2D grid in this context, because our n dimensions here are 2. It just creates a virtual. The keyword here is virtual. It creates a virtual 2D grid based on your current number of processes, MPI processes. Okay, so in this case, it will create a 2D grid, something like this over here. If let's say you specify if your MP is 12, so in this case, it will create a 3x4 grid for you. And each process will have a 2D coordinate. All right, so that's what MPI cut create does. And then you can use the other functions, MPI cut coordinates. MPI cut coordinates now, as mentioned in the file over here. Okay, the example. Okay, so if you look up here, I think early on we covered a few functions. MPI cut coordinates returns you pass in the communicator. So now you don't pass in combol anymore, because now you need to pass in the virtual topology. The virtual topology is described in this communicator. So you pass in the communicator com2d, you pass in your current rank. Okay, you pass in your current rank. So let's say if my current rank is 4. So my current rank is 4, and my dimensions is a 2-dimensional grid. What is my coordinate value? All right, so it will return you the coordinate value. So what is coordinate over here? So coordinate is actually a where's the coordinate variable? Here. So you pass in a coordinate, you return you your 2D coordinate value. That's why the coordinate is also a 2D I mean, obviously, because it's a grid, 2D grid, so your coordinate is also a 2D array. I mean, not 2D array, my apologies. Your coordinate contains two elements. The array contains two elements. The first element is the row value. The second element is the column value. Okay, my apologies for the earlier mishap. All right. So let me just delete this. Okay. Now, so this is the coordinate is returned into the chord array. The chord array over here. All right, then you can print out. As you can see over here, you can print out. You'll print out the row and column value of the particular rank. So for each rank, you will have your row and column value. Exactly the same thing that we've done over here. All right. Now, cut rank was not discussed inside this PDF file, but if cut rank is the reverse of MPI cut coordinates. So cut rank, exactly this cut rank, instead of returning you your coordinate position, it returns you a rank. So you pass in the coordinate value, you pass in the I and j value, it returns you your rank value. So in essence, what MPI cut rank does, okay, what MPI cut rank does is it translates the row and column value into a 1D value. So which means that your rank is equals to what? Okay, your rank is equals to your row, your row position. So sorry about this, maybe let's do this again. Your rank is equals to your row position multiplied by the column width plus the column position. So in this case, let's do again. So let's say 1, 2. So 1 times 4 plus 2 is 6. This is what exactly MPI cut rank does. It returns you your one-dimensional rank into this variable over here. Now, because why we have this function is because sometimes if the reorder does actually, if MPI cut create does actually reorder, your cut rank can be different than your actual rank. So normally we do this function as a failsafe, but in my experience, most of the time the cut rank is, the 1D cut rank is equivalent to your actual 1D rank value over here. Okay. Now, the important function is here, cut shift. Now, the whole idea of doing Cartesian topology is that you want to know who are your neighborhood nodes. In this case, we're looking at our top, bottom, left, and right neighborhood nodes. So that's where we use the cut shift function. So if you go back to the description in the PDF file, cut shift, okay, takes in 4 arguments. Okay, the last 2 are the output arguments. All right, so you pass the communicator, the direction, and the displacement. So let's look at the code. So the first argument is the communicator. Again, guys and girls, please do not pass in the global communicator MPI combo. Now you have to pass in your virtual topology, because the virtual topology describes this communicator. You pass it into this communicator, then look at these 2 variables over here, or shift row, shift column, and displacement. Where are these 3 constants or variables declared? If you refer back to the early part of the code, they are here, symbolic constants. So what does these 3 variables imply? Let me explain to you all. Currently, shift row is 0, shift column is 1, displacement is 1. So when you do cut shift, when you want to know who is your neighborhood row, it should be 0. For rows, who you want to know, if you want to know who is the top and bottom nodes, who is your adjacent top and bottom nodes, cut shift, the second argument should be 0. So in this case, you can either put 0 or I put a symbolic constant here. Just, I mean not me, and the sample code uses a symbolic constant. So I'm just referring back to the same method they use over here. All right. And shift column, if you're going to see, if you want to know who are your left and right nodes, not top and bottom, left and right nodes, then you call cut shift again, you pass in 1. Or in this case, shift column, which is a symbolic constant, which sets the value to be 1. Okay. All right. Now, the displacement here is interesting. If I put 1, which is what this symbolic constant carries, which means that I'm looking at my immediate neighbors. Immediate. So I'm only looking at who are my immediate neighbors over here. I displace by a factor of 1. But if I displace by a factor of 2, I'm looking at who are my neighbors here. All right, so you can change the displacement vector. So it not necessarily has to be your immediate adjacent neighbors. You can displace it further to find your neighborhood nodes. So as you can see, it's a very powerful function. So generally, what card shift does is it just does some simple calculations to compute based on the current topology and based on the and for each node, who are your relative left and right nodes. And it returns you back. So the last two arguments, as mentioned in the slides here, the last two arguments are your left and right nodes. So it returns you who is your top node, who is your bottom node if you are looking for row shifting. For column shifting, who is your left node and who is your right node. So after doing this, each process, so you see, when you do card shift, notice that it doesn't ask for the rank value, your current rank value, because inside card shift, they can get the current rank value internally. So don't worry about that. Okay. So card shift just needs to know the topology, whether it's 2D or 1D or 3D topology. They pass in a topology communicator inside here, which you have gotten it from the MPI card create. You specify whether you want to know who are your top or bottom neighborhood nodes or your left and right neighborhood nodes, how much displacement you want, and then you will get your top and bottom neighborhood nodes written in these variables and your left and right neighborhood nodes written in this variable. That's why I put the I and the J over here. All right. And then the print function over here prints out the global rank. So each MPI process will print out its rank, its Cartesian rank, its current 2D coordinate value, and its left, right, top, and bottom neighbors over here. That is what the sample code provided to you all in task 1 is doing. Now I'm going to explain this commented code later on. Okay, so let's save this code now. All right, so let me compile the code. Okay, so it's T1, and then after that LM, because we are using a square root of the function, so it's good to put a math function inside there. So no problems. So I'm going to use MPI. Now you see, if I were to just type MPI run 12, NP12, I want to use 12 MPI processes, and I specify MPI out, I'm going to get an error over here. It says that I do not have enough slots because this virtual machine is running on 6 logical processes, which means that I cannot run more than MP6 over here. But now you can force it to run because for data parallelism, if you run more processes than the available number of actual CPU cores or logical processors on your machine, you are going to slow down the overall parallel computation. That's why MPI puts that fail-safe code inside there. So the fail-safe logic inside there, sorry. So, but if you really want to force it, you can use the following command, -over subscribe -NP now 12. Now you can force MPI to say, I don't care, I want to do 12 processes over here. But I'm not focusing on performance. I'm looking at logical behavior. Okay. So now if I run this now, okay, I'm going to get the entire results over here. So now let's look at them. Let's analyze these results with respect to our grid. So it created a 4x3 grid over here, a 4x3 grid. So, okay, I didn't specify a common argument. So by default, MPI dimensions create, return me a 4x3 grid. Okay. All right. So now let's look at the PDF file. Let's look at the PDF file over here. Let's look at the 4x3 grid. 4x3 grid over here. Okay. So if I go to the file, maybe I should make it smaller. Okay. And then let's go over here a bit. Let's zoom to the right. Okay. All right, here we go. Nice. So let's pay attention. Okay, let's look here. Ups. My apologies. Now let's look for rank 4. Okay, I'm going to only highlight rank 4. Okay. And I'm going to open up the PDF file again. So rank 4's coordinate on the grid here is 1, 1. So exactly, my global rank is 4, my card rank is 1, my coordinates, after calling MPI card coordinates, I got my 1, 1 value here. After calling card rank, I got my rank value 4 over here. After calling card shift for the row and the column, you can see that, okay, sorry about that. Okay, you can see that the left is 3, correct? You see, it returns you the rank. Okay, it doesn't return you the 2D position. You can calculate that manually later on, or okay, but it returns you the rank of the neighborhood node. So my neighborhood node, my left neighborhood node is 3, my right neighborhood node is 5, my top neighborhood node is 1, my bottom neighborhood node is 7. That is how MPI create, MPI coordinate rank, MPI Cartesian rank, and MPI card shift actually works. So now you have a virtual topology whereby each process, each MPI process now knows who are their immediate top, bottom, left, and right nodes. Okay, using the MPI virtual topology functions. Now, if I were to be a bit mischievous, let's say I change the displacement to 2. Okay. And then if I were to run the code again, compile a code. Okay, compile a code and run the code again. Now notice that for rank 4, things have changed a bit. Okay, with reference to this, for rank 4, my left is now negative value, my right is now negative value, my top is also negative value, my bottom is 10, process 10. Because now the displacement is 2, it jumps by 2 values. Because we're not doing reordering, sorry, my apologies, we're not doing periodic, our periodic is false, so we will get negative. Negative 2, in the PDF it shows negative 1. If you look at the PDF file, it shows negative 1 for certain cases, if I'm not mistaken. They didn't show it inside here, maybe the other example they could show it. I think here. Did they show? No, they didn't show. But sometimes it will show negative 1 is based on the MPI implementation. Here we are using Open MPI. When MPI detects a neighborhood node that doesn't exist, it returns you negative 2. If you go back to the MPI header file, if you look at the MPI header file over here, okay, it says that MPI, it will return you MPI process null, which is negative 2 in this case. In Open MPI, it returns you negative 2. Other MPI implementations may return a different negative value. So in the sample, in the PDF file that we are referring to over here, I think, if I'm not mistaken, one of the examples at the bottom, they actually show that the nodes are there. You can see over here that it returns you they put a negative value over here. Yeah, I think here they put a negative value. Yes, a negative 1. Okay, that means that the MPI process null. There's no neighborhood process over here, but this is subjective. The negative value is subjective to the MPI implementation. We are using Open MPI, so you return you negative 2. All right, so you can check if the node is less than 0. If the return left is less than 0, which means it doesn't exist. As simple as that. Okay, so that's how we can use MPI card shift, card create, coordinate rank, and Cartesian rank. So it's very easy. All right, so I'm putting back the displacement 1 again. It's very easy over here to do that. I mean, you can argue, yes, I can calculate everything manually. I don't need to use the MPI virtual topology functions. I can manually calculate like what we did in our assignment 2 description. Perfectly fine. All right. So now, how do we make use of this? How do we make use of this? This is what was provided in the task 1 code also. Okay. Now, in task 2, you are asked to perform a task over here. So I will let you all read this on your own. But what I'm going to do here, all right. Now, let's say if I were to comment out this code. This code is pre-written for you all. Okay. on the comment on this code. I do not want to have too many printouts. So I have a MPI B. I declare a bcast value -1. If my card rank is 4, MPI broadcast value 4, and I broadcast this value to everyone within the topology over here. So what do you think will happen? What do you think will happen? All right. So let's compile the code. Is it saved? Yes, it's saved. Okay. If I have to compile the code now, and then if I have to run the code, you can see all processes will get the broadcast value. So it's not that you can't assume that, oh, because this COM2D is specific to only the adjacent nodes. No. The virtual topology communicator still encompasses the entire 2D grid. Okay, let me repeat again. The virtual, the COM2D here, which is returned to you by as an output argument in card create, still covers the entire all processes in a 2D manner. So when I call broadcast value, I'm broadcasting to everyone. So then you'll be asking, well, okay, how do I then make use of the Cartesian topology over here? Okay, that's where this next chunk of code comes in, which will help you a bit in the lab activity. Okay, so let me explain this code to you all a bit. Okay, so what I have over here, I'm going to do a non-blocking send and receive. Normally in a virtual topology, so far in my experience, I normally use non-blocking send and receive just to be safe. Okay, you can actually get it working with blocking send and receive, but in my experience, I prefer using non-blocking send and receive. Okay, and then with the wait all at the end. Okay, so if you're not familiar with non-blocking send and receive, please refer to week 7's pre-lab video. I think there's we went through this in quite in detail. All right. Okay. So inside here, oops, sorry. I've declared the request arrays and the status arrays. I'm not going to go in detail about what these arrays do. We have discussed this about this in the past video already. I'm going to generate a random value. I'm using ren_r, and then I pass in a seed value over here. I put a sleep here because I'm running multiple MPI processes on the same machine. So if I don't put a sleep over here, they will all generate the same value because the time is the same time. Okay, so I put a sleep here purposely that rank 1 will generate a different random value, rank 2 will generate a different random value based on this on the seed value over here. All right, so that's why I put a sleep over here. So of course this may slow down your program, but it's okay. We are doing this to visualize the program over here. Okay, and then I call MPI iSend. So you can see now each MPI process is doing these functions. Each of them, if I'm running 12 MPI processes, each of them is doing them. Each of them is doing the operation over here. Now, each MPI process is generating a random value and is sending the random value to its top, bottom, left, and right nodes. So where do I get these 4 variables? From your card shift functions over here. All right. Okay, and then I'm using the COM2D communicator. And then I update my send request. And then the same thing, I have 4 receive variables. I call iReceive. I call iReceive from top, I call iReceive. So which means each process wants to receive the value from the top neighborhood, bottom neighbor, left neighbor, and right neighbor. And who are the top, bottom, left, and right neighbor ranks? We use the same variables over here. And then the receive request here. And then I call wait all. And after that, I print out the values over here. So now let me comment out this code. Okay. So let's look at this. Okay. So this code was not given, I mean, inside the PDF file in task 1, but I will. So you see the task 1 code stops up to here. All right. But to help you in task 2, okay, this is not solution of task 2. This is just a helping code, starter code a bit. I will provide this code to you all in the video description in YouTube, or also I'll put this code into the pre-lab video section in Moodle for week 9. Okay. All right. So when I run this program now, I compile and run this program. Okay, let me just clear this. I'm going to compile the code again. run again. So now it will take some time because it's a sleep. It will take about 12 seconds to complete. So everyone is running now. Okay, good, good. It's running, it's running. Okay, okay, done. Now let's pay attention. So let's open up. I need to open up. Maybe I have to go a bit to the side here, squeeze a bit. Again, go back to the communicator. So we have our 4x3 grid. Okay, so let's look at, okay. So let's look at P4 again, global rank 4. Global rank 4. All right. And let me open up the PDF file again. So global rank 4, our neighbors are, our top neighbor is P1, bottom neighbor is P7, left neighbor is P3, and right neighbor is P5 for rank 4. So you can see rank 4 generated the following random value, 33. It received from the top 92. Who's 92? It received the value 92 from the top. Who's the top? P1. What is P1's? Look at P1's generated random value, 92 over here. So you see, it makes sense. All right. And then rank 4 received the bottom value, 22. Who's the bottom neighbor to rank 4? Rank 7. Rank 7 generated the value 22 over here. So you see. And then who is the left neighbor? It received 51 from the left neighbor. Who's the left neighbor for rank 4? P3. P3 generated the value 51. And then finally, who received the value 39 from the right neighbor? Who is the right neighbor? P5. P5 generated the value 39. Can you see? So that is the how you can actually use and virtual topology to help you communicate to receive value. So you see, when rank 4 did this, at the same time, okay, at the same time, let's look at rank 7 now. Okay, let's look at rank 7. Okay, sorry, let me highlight it properly. Okay, rank 7. Oops, dang. Okay, all right. So if you look at rank 7, so rank 7, you see rank 4 got the value, rank 7 generated the value 22. Okay, and rank 4, this value 22 was sent to rank 4. You can see rank 4 received the value 22. At the same time, rank 7 received the value 33 from the top. Who's the top? P4. P4 generated 33. So you can see each process is able to, at the same time, send and receive messages with its adjacent nodes. And that you can achieve that by using the MPI virtual topology. That is what this code and the first part of this video wants to explain to you about. All right. Now the second part of the video, I'll continue in the same video. I do not want to create another video, so this might prolong the video a bit, but the second part of the video is very short. Okay, so I hope this gives you all an idea. All right, and if you look at task 2 requirements for the lab, okay, so what task 2 is asking you to do, each process generates a random prime number and exchanges the random prime number with its adjacent process. Upon exchanging the random prime numbers, each process compares the received prime numbers, and if the prime numbers are the same, each node, the node will log into a log file. Now you may be thinking, hey, isn't this very similar to the assignment 2? More or less, but not exactly. You see, here each MPI process generates a random prime number. So it's not only a random number, but a random prime number. So I trust you all will know how to generate a random prime number. Okay. Okay. So don't overthink this one. Okay. It's actually very easy. You generate a random number. Sorry. You generate a random number, and then you check if the number is a prime number. If it's a prime number, then you keep the number and then you exchange the number with the adjacent processes. So as straightforward as that. Okay. And then once you exchange, so it's in fact, I've kind of like provided you all a partial solution here already. All right. But guys and girls, this is actually not a very clean code. It's better if you can put this into an array and then you can do a for loop here. So I hope all of y'all would implore how to actually convert this into a for loop. I mean, it's very easy. All right. Yeah, I mean, at this stage, I trust you have you all can do this. So I mean, it's not that if you do this, you're going to lose marks or anything like that, but it's not very clean, in my opinion. All right. So you can actually use a for loop. You can put all of this into an array, and then from there you can do a for loop with I send and I receive. All right. And then you can do the MPI wait all outside the for loop. Okay. So this is very partially solves. I mean, the communication is already partially done for you all here already. And then you just, once you exchange the values, if the prime numbers are the same between the adjacent nodes, then you log it into a text file. Now, but this is not what the assignment wants. If you look at the assignment says what? The assignment says, if the generated temperature value exceeds a threshold, the node will then send a request. So there's a difference between what the assignment 2 wants and what we are doing in lab week 9. Although it falls within a similar domain, but there are some slight differences. Okay, so here each node generates a random process, and then it immediately exchanges. Sorry, let me undo my last statement. Each node generates a random value, in this case a random prime number, and then it exchanges the random prime number with the adjacent nodes. And then once each node receives the prime numbers from the adjacent nodes, then you will check whether or not the prime numbers are the same for logging. In the assignment, is different. In the assignment, only if a temperature value of a node exceeds a particular threshold value, then only the node sends a request to get the adjacent temperature values. So you may argue, okay, I mean, I can still implement this method for assignment 2 and claim that, well, in a way it does fulfill to some extent the requirements, but not exactly the requirements. But you will not probably get the D or HD for that particular section of the marking for if you do it this way. So we hope you try to carefully study how you can implement this method, okay, for assignment 2. This method is, you can always consider this technique, okay. I've already kind of provided some supported code here already, so in a way it's really helping you all. Apart from the loop, I didn't do a loop here, so you might need to implement a loop for the task in assignment 2 also. But what I meant to say is that this method is like a baseline method. It's like, okay, it's something to get you at a base level, and then from there you can try to figure out how to actually update the code or revise the code to fulfill the assignment specifications. Okay, so that's what I wanted to explain to you. Okay, so I hope by doing task 2, you will now be in a much more better position, okay, a stronger position to complete the assignment 2 already. Okay, now task 3, the second part of this video, is about master slave MPI. So I'll quickly go through this video because it's much more simpler. Okay, now, so I've given you all a sample code over here, and now before I go to task 3, sorry, in the file by Mary Thomas, the PDF file, Mary then goes to the extent to discuss how you can use MPI, how you can use MPI. Mary goes to the extra mile to explain how you can use MPI Cartesian sub to partition a communicator into subgroups. So what Mary did was, she actually provided the code and the description and the sample code on how, if you refer to page This is for 1D. This is for 2D. Okay. Here. Yeah. So how you can actually create a Cartesian topology, and then within the Cartesian topology, you call cart sub to actually create a subgroup within the Cartesian topology. So now when you call MPI broadcast within the subgroup communicator, you will only be restricted within the 3 processes over here. All right, so this is something for you all to explore on your own. You don't necessarily need to do this for the assignment, okay? But this is just something for added knowledge for you all to learn, okay? So this is there for you all. This is there in the PDF file. This PDF file will be provided in the pre-lab section for assignment. For week 9 in Moodle for FIT3143. Okay, so I'm going to close this file now. I'm going to close assignment 2. I'm now going to focus only on task 3. Task 3 is based on a master-slave operation. Okay, so what is master-slave? So in MPI, you can split a communicator. So let's say in MPI, all right, so let's say you have 1, 2, 3, 4, 5. Okay, so you got P0, P1, P2, P3, P4. So all of them now are under MPI COM Okay, what you can do is you can split the communicator into 2 groups. Let's say like you can create a master and you can create a set of slaves or workers. Okay, slaves or workers. All right, and each of them will have their own new communicator for master and a new communicator for slave. And that is what task 3 and task 4 is going into. So quickly, I'll just go through into task 3's code. So I'll close task 1. Okay, so in task 3's code is very straightforward. I have 2 functions, master IO, slave IO. Master IO takes in 2 arguments, a variable master communicator of type MPI communicator, and then the original communicator, a slave IO, a variable of the master communicator and the input communicator over here. So I will explain to you all later on how this code actually works. So in the main function, you can see over here, it's very simple, this code, okay? So MPI init comrang, okay? Now here, this is where the interesting part happens. I did comsplit. So what is comsplit? This is a new function. So today you're learning quite a lot of functions. You have learned MPI dimensions create. You have learned MPI Cartesian create, MPI cart coordinate, MPI cart rank, MPI cart shift. And now that is for virtual topology. Now let's say we want to split your communicator into 2 groups. All right, so you can do MPI comsplit. So MPI comsplit, as the name implies, okay, creates a new communicator based on colors and keys. So what is colors and keys? Let me explain to you all. Okay, so colors and keys. So the first argument is your original communicator, your COM. Second one is the color. So what it does is, in very simple, okay, the color means that here I'm splitting the processes into 2 groups. So which means I got group 0 and group 1. So which means how many colors do I have here? 2 colors. If I'm going to split into 3 groups, okay, if I'm going to split into 3 groups, let's say I got P0, P1, P2, P3, P4, P5, P6. Let's say I want to do this, split this 1, 2, 3. So this will be 1 group, second group where number, third group number, fourth group number. So how many colors do I have here? I have 4 colors. That is the whole idea of colors. All right. And then the third argument is key. The key is, how do you determine the rank values within each color? Do you want to use back the original rank values, or do you want to use back from a starting rank value? So not original rank value. Do you want to refer back to a particular reference rank value? Or do you want to reset the rank value, which means you want to create like a 0 and 1, 0 and 1, and 0 and 1 here, and then this is 0 over here. So within this communicator, you will have different rank values. So which means that you will have global rank values. These are all your global rank values. Okay, these are all your global rank values. And then this one is your local rank values respective to your custom communicator or to your split communicators over here. All right. So by default, normally not say by default, but my experience, normally I'll put 0. All right. So that's why. So they see within each subgroup, the processes are ranked in order defined by the value of the argument key. So you pass in the key value, then you will take the key value and then you will increment the rank value. Okay. With ties broken according to the rank in the old group. So by default, we'll put 0. All right. Okay. So this is ComSplit. So based on that, you can read more for more. It's actually a very powerful mechanism for dividing a single communicator into a group of processes. And in the past, you can actually, not in the past, you can actually combine this with Cartesian topology for your assignment too. All right. So if you are adventurous, you want to do more, you want to demonstrate more for your assignment, for a report, especially for a report, you want to have a more impactful report. Not necessarily saying that doing ComSplit and topology will definitely help improve the impact of a report. But if you feel that you would like to demonstrate that you are doing this, then you can consider implementing ComSplit as together with topology for your assignment. It's not compulsory. Okay, let me reiterate, it's not compulsory, but it's something that you can consider if you feel that by doing so, you can actually discuss more in your report. Okay. Now, so going back to the code over here, so we have ComSplit. I pass in the first argument, the origin, the current communicator, MPI ComWorld. Now you see here, look at this argument, the colors. This is not, remember, be careful, this is not single equal. This is not single equal, double equal, which means what? This is a condition. Condition, true or false? True or false? Okay, so this return me 0 or 1. So I will check each process when they call MPI ComSplit, they will check, is my rank 0 or not? If no, the color, the non-rank zeros will belong to color 0. If the rank is 0, it will belong to color 1. So let me explain to you all this simple code here. All right. Okay. It's actually very interesting. A very simple analogy, but with very meaningful impact. So let's say my NP is 6. Okay, so I have P0, I have P1, I have P2, I have P3, I have P4, I have P5. All right. So now from here, each process, each MPI process will actually execute line 16, MPI ComSplit. What happens is that each of them will also execute this chunk of code here. This instruction, rank equal 0. So which means each of them will execute line 16. So what do you think will be the outcome for rank 0 here? The outcome, this is a condition. It will return you true or false. True means 1, false means 0. So for rank 0, this will be a 1. For rank 1, what is the outcome here? My rank is 1. 1 is not equal to 0, so which means it's a false. So it will be a 0. Rank 2 will be a 0. Rank 3 will be a 0. Rank 4 will be a 0. Rank 5 will be a 0. That's it. So we have 2 colors over here. 2 colors over here. Okay. So which means that now rank 0's communicator will only contain one process, which is rank 0 itself. The rank 1 to rank 5 will be in another communicator. So a different communicator. So you got communicator 1, communicator 2, and they will have their own local rank values, 0, 1, 2, 3, 4. Okay, so the new communicator for rank 0 is com1. The new communicator for ranks 1 to 5 is com2. So you check if rank 0 will call the master IO function, pass in the global communicator and the new communicator. The rest of them will call the slave IO, will pass in the global communicator and the new communicator created. Inside here, what happens is very simple. The slaves will send a message. The slaves, I mean, this code is not really a good code, because the input communicator here, yeah, just sorry. I mean, sorry, it's not the best of code, but it's a simple example. You can see it will print out its own local rank value. All right. And then it will send a message to the master communicator. Okay, it will send a message to the master communicator over here. So where is the master communicator declared? All right, the master communicator is declared. Wait a minute. I think there could be a simple bug in the code here. Just 1 second. Oh, sorry. My apologies. There's no bug to the code. My bad. I slightly misinterpreted the code. The master communicator here is actually your MPI convol. Okay, MPI convol. So in this case, the master communicator here is equals to MPI convol, just to make it very clear to all, to you all. Okay. All right. So which means that you are sending to rank 0 the master using MPI convol, and the master rank 0, which runs the master IO, receives the messages, okay, using the MPI convol based on I equals to 1 to size. That's about it. That is what this code is doing. I mean, it's I would like you all to go through the code. Okay, so let me just clear this. Let me just compile again lab T3 task 3 code. Okay, so if I have to run this now with 12 processes, so you can see the slaves starting from 0 to 10. There are 11 slaves. Okay, so the slaves now, they're all in one color. All of them are in one color, this particular color. Okay, color 0, and they have their own local rank 0 to rank up to rank 10. All right, they are all sending a message to the master. The master then gets a message and prints out the message on screen over here. That's what this code is doing. MPI com split. Okay, and then what we want you to do, okay, what you want you to do is to then, okay, what you want you to do is to then extend task 3 to accept 3 types of messages. So you can try this as part of the assessment. So for FIT9's lab, task 1 and task 3 are worked examples. Go through them, run the code, compile the code, put your output into the eFolio file. But you need to complete task 2. Task 2 and task 4 is assess. Sorry, task 2 and 4 are actually assessed. Okay, and then if you have time, you can try out the bonus activity, which is for 3D cut, MPI cut. So you can find some resources online to actually help you out with this one here. So that's it for the PLAB video. I hope it has given you a very good idea on how to do virtual topology and master and slave with MPI. And after this week's lab, I sincerely believe that you have all knowledge to actually complete assignment 2 already. Now, let me reiterate. It is not compulsory for you to use MPI virtual topology or master slave to do assignment 2. If you feel it helps you in doing assignment 2, then by all means, we do encourage you all to give this a go for assignment 2. But there again, please remember what we are helping you here in, the sample code that we are given you here for task 1 and the sample code that I've given you here in the lab T2 code, especially this example over here, doesn't, sorry, my bad. I think I've accidentally, okay, all right, T3, oh, my bad. Okay, my apologies, T1 code. Okay, doesn't necessarily mean that this is the right method to do for assignment 2. Okay, assignment 2, the method is slightly different, so you can try to look at the assignment requirements and then from there give it a go. Okay, So that's about it. Thank you very much.